So thanks for coming. I'd like to thank myself for inviting me. The title of the talk is New Algorithms for Heavy Hitters in Data Streams. This is based on several recent joint works with Arnab Bhattacharya, Vova Braverman, Steve Chestnut, Palash Day, Nikita Ivkin, Jelani Nelson, and Jungyu Wang. Okay, so we're going to talk about a fundamental problem in data streams called finding heavy hitters or frequent items. And we're going to give more space-efficient algorithms for this problem. So let me recall the streaming model. We're given a stream of elements, A1 through AM. Each element is, without loss of generality, drawn from the set bracket n, which is the first n positive integers. And we're going to assume the length of the stream m is polynomially related to the universe size n. And the stream of items is presented in an arbitrary order. Okay, and we're interested in algorithms that make one pass over the stream. And we'd like to minimize the space complexity in bits for solving a particular task. Okay, there are also other resource objectives like minimizing update time, query time, etc., that we'll get into. We're going to be discussing problems that concern the frequencies of items. Okay, so let f sub j be the number of occurrences or the frequency of item j. The problem we're going to study is the heavy hitters problem. Okay, so what we'd like to do is find those items j for which the frequency f sub j is large. Okay, where there are various different meanings of the word large that I'll get into. Okay. So one notion of being large is what's called the L1 guarantee. So here you'd like to output a set which contains all items j whose frequency fj is at least phi times m. Okay, recall m is the length of the stream. Phi is just an input parameter. Okay, so maybe phi is 0.1, and you'd like to find those items that occur at least 10% of the time. And you don't want false positives, so your set should not contain any items j whose frequency f sub j is at most phi minus epsilon times m. Okay, so here we relax the problem a little bit. We have phi m versus phi minus epsilon m. If epsilon is very tiny, like 0, this is a very hard problem. So this is why we relax the problem a bit. Okay, so that's the L1 guarantee. There's also the notion of the L2 guarantee, which is sometimes stronger. So here, define the second moment, capital F sub 2, to be the sum of squares of item frequencies. Okay? So analogously to before, what we'd like to do for the L2 guarantee is output a set which contains all items j whose squared frequency is at least phi times f2. And we don't want to output any item j whose squared frequency is at most phi minus epsilon times f2. Okay? I want to mention that for some settings of parameters, the L2 guarantee can be much stronger than the L1 guarantee. So here's a typical example. Suppose the frequency vector looks like the following. The first item occurs root n times, and all the other items occur once. Okay? Then item 1 is an L2 heavy hitter for constant phi and epsilon. Why? Because if I square this frequency, I get n, and I add it to the sum of squares of 1, n minus 1 times. So the f2 value is about 2n, and this squared is n. So if I set phi to be 1/2, this is a 1/2 heavy hitter for the L2 guarantee. On the other hand, for the L1 guarantee, this frequency is only root n, and the sum of the frequencies is about n. So I'd really have to set phi to be very small, like 1 over root n, to guarantee I find this with the L1 guarantee. Yeah? OK. So the outline of the talk is as follows. I'm going to discuss two results. First, I'm going to give an optimal algorithm in all parameters, n, phi, and epsilon, achieving the L1 guarantee. If you're familiar with classic data structures like Misra and Gries, we're actually going to do better than Misra and Gries. And then in the second part of the talk, I'm going to discuss an optimal algorithm for the L2 guarantee. It's almost optimal in all the parameters, but I'm going to focus on constant phi and epsilon. Okay, it's not entirely optimal in terms of phi and epsilon. Okay, so let me start off with the algorithm for L1 heavy hitters. And let me review a classic data structure for this problem called the Misra and Gries data structure, which is rediscovered several times. So how does it work? So you have a list of C, which you set to be order 1 over epsilon, pairs of the form key comma value. Okay? And given an update to an item I in the stream, so I see an insertion of item I, what do I do? If I occurs as a key for some pair in this list, then I look at its value and I just increment it by 1. Okay, so I'm tracking the count of item I. Similarly, if I does not occur in the list as a key, but there are fewer than C pairs in the list. Okay, so what that means is this list is initialized to just a bunch of empty pairs. And sometimes in the stream, I might have just empty pairs out of these C possible pairs. So if I have room to put I, then I put the key I comma 1 in the list. I start tracking it. Okay? And the more interesting case is the following. So if I have update I, and it doesn't appear in the list, and there's nowhere to put it, because I already have C pairs, then what do? Well, I look at all of the pairs in the list, and I subtract 1 from all of their values. Okay? And then some of them might now have value 0, in which case I remove them from the list. Okay? Yeah, so the basic observation is the following, that you can get good estimates to each frequency by charging its updates to values where that were decremented in this third step. So let me explain that. So suppose at the end of the stream, item I does not occur inside of this list. Okay? This means that for each update to item I, suppose that I was in this third case, this means that actually I'm subtracting off C values, C updates in the stream, 1 from each of these keys, instead of putting item I into that list. Okay? So basically, I can charge the updates to item I to see other values inside of this list. Okay? Alternatively, if item I is inside of the list, and I subtract 1 from its value in this third step, well, I'm also subtracting 1 from C minus 1 other values inside of that list. Okay? So I can always charge its updates to at least C minus 1 distinct other updates of stream items. This is the intuition. Okay? Now I have F sub I, that's the frequency of item I. I have that number of updates to it. Okay? And each time I'm charging C minus 1 other updates in the stream. So Fi times Ci minus 1 has to be less than M, right? The total number of updates. Okay. But we set C to be 1 over epsilon, which means that the frequency of item I is less than epsilon M. Okay, so if item I does not appear in this table at the end of the stream, it means that's because its frequency was small. Okay, this is a standard Misra and Gries. Okay, and the same kind of reasoning also applies to the value of the item. Okay, so suppose the item I is inside of this list at the end of the stream. Well, we know that the frequency, the value of the item I in that list, the frequency is always going to be less than the actual frequency, right? Because we could insert it We only insert it when it actually occurs in the stream, but sometimes we're decrementing it. But just like before, how many updates to that item are we not accounting for in the value in the table? Well, it can be at most epsilon m. Okay? For each update we're not accounting for in the table, we can charge it to c minus 1 decrements to other values, updates in the stream. Okay? So for each update, it's the same formula, actually. The number of updates that I don't account for times c minus 1 has to be less than m. So in total, I have at most epsilon m updates that I don't account for. And so this gives me a guarantee that for all items that do appear in the table at the end of the stream, I have an additive epsilon m approximation to their frequency. Okay? Any questions about this? Okay, so this is the Misra Gries data structure. This is what's been used for finding L1 heavy hitters in a lot of places. What is the space complexity of this data structure? So I have C counters, okay, order 1 over epsilon. And each one, I'm maintaining a key, the item identity. I have a pair of items, a pair of things. I have an identity and a value, a count. The identity can be specified with log n bits. Assuming the stream length m is at most poly n, the count can also be specified with log n bits. Okay, so the space is c times log n, or order 1 over epsilon times log n bits. Okay. Now, what is the complexity of specifying the output to this problem? Right, we want to find all of those heavy hitters, all of those items which occur at least phi times m times in the stream. Right, the frequency is at least phi times m. How many items have frequency at least phi times m? I mean, there can be at most 1 over phi such items, right? And each one I have to specify its identity. So 1 over phi times log n is a natural lower bound. It's the lower bound on the output size to specify all the heavy hitters. So if phi is on the same order as epsilon, then actually this is an optimal algorithm just because the output size has the same space complexity. Yeah, makes sense? Okay. But what if phi is a constant and epsilon is really small? Okay, so you have a few heavy hitters and you want to estimate their frequencies very accurately. Okay, so then Misra Gries, the space complexity, if I plug in epsilon as 1 over log n, is giving me a log squared n bit space algorithm. On the other hand, the space complexity of representing the output is only log n bits, right? Because I can only have 2 items that have frequency at least 1/2 times m. Okay, so there's a gap here. So yeah, this is what we study here, and we in this first part of the talk, and we're going to close this gap for L1 heavy hitters. Okay, so what we obtain is a new algorithm for L1 heavy hitters, which is optimal. The space complexity, you still have this 1 over phi log n to specify the heavy hitters. But this leading order term, or this other term, instead of being 1 over epsilon log n, is 1 over epsilon log 1 over phi. Okay, and we can show a lower bound that this is optimal up to a constant factor. And just plugging in the example that I just mentioned, if phi is a constant and epsilon is 1 over log n, then now this is log n plus log n, and we'll get the optimal log n bit bound instead of the log squared n bit bound of Misra Gries. Okay. So I'm just for simplicity, I'm assuming the length of the stream m is polynomially related to n. For general stream lengths, there's an additive log m in both the upper and lower bounds, which is also, okay, so that's also optimal. And also the update time. So when I see an update in the stream and I need to update my data structure, I can do that in constant time. And when I have to output these at most 1 over phi heavy hitters, I spend constant time per outputting each one of them. Okay, so I get constant updating reporting time, provided the stream length is sufficiently large. Okay, at least say polynomial and 1 over epsilon. Okay, so this is these are the results for the first part of the talk. Yeah, let me know if you have any questions. To show this new algorithm, I'm just going to first start with a much simpler algorithm, which almost achieves that space complexity. So I'm going to start off with an algorithm which has 1 over phi log n. That's just to specify the heavy hitters. And the other term is going to be 1 over epsilon log 1 over epsilon. Okay, now I mentioned the optimal thing was 1 over epsilon log 1 over phi. So it's slightly off. But if you think of this example where epsilon is like 1 over log n and phi is a constant, this would just be log n log n as opposed to log n. So it's close to optimal already, and it's actually quite simple. Okay, so the idea here is just to run Misra and Gries. You're going to use the same number C of key value pairs. Okay, this 1 over epsilon pairs in my list. But you're going to compress each pair. Okay? So how are you going to do that? So we're going to compress the values, right? So we have a key and a value. The value is like the number of, approximation to its frequency. So these values can be, up to log n bits because the stream length is poly n long. But what we're going to do is we're going to sample uniformly order 1 over epsilon squared random stream positions. Okay? And we're just going to run Misra and Gries on these sampled stream positions. Now, if you've worked in data streams, this is a bit different than the usual sampling where you sample items. You sample a subset of items and run the algorithm on that. Here we're actually sampling the updates themselves, the actual stream positions. Okay, and how do you implement sampling 1 over epsilon squared random stream positions? Well, for each item, I independently include it in my sample stream with probability p, which is a constant c divided by epsilon squared times m. Okay, this assumes that you know a bound on the stream length m in advance, but you can also get rid of that assumption. So the observation here is if I sample 1 over epsilon squared random stream positions, then simultaneously for all items I, if I look at the frequency gi in the sampled stream, and I look at gi over p, okay, so the expectation of that is just the frequency, the original frequency, okay? It's an unbiased estimator. I look at its deviation from the actual frequency, f sub I, and this differs by an additive epsilon m. Okay, so just to illustrate techniques in data streams, I'll just show why this is true on the next slide. But it means that we can actually run Misra and Gries on the sampled stream. Okay, all the frequencies are preserved up to additive epsilon m. And now note that if my stream length is order 1 over epsilon squared, I'm just sampling a small number of positions, then I can't have many distinct items in the stream. Right? I mean, I can have at most number of updates distinct items. So I have at most order 1 over epsilon squared distinct keys, something that actually gets sampled. And so for those, instead of storing their actual log n bit identity, I can hash the universe of all identities n down to, say, order 1 over epsilon to the 4th. And with constant probability, none of these order 1 over epsilon squared distinct keys will have the same hash value. They'll all get perfectly hashed. Okay? So there's sort of two ideas here. One is make the counts in Misra and Gries smaller. So now I only need log 1 over epsilon bits to store the counts, because the stream length is at most 1 over epsilon squared. And the other idea is that make the keys description smaller. Now it's only going to be log 1 over epsilon bits. Any question? You do want the actual keys, not these hashed keys, but I'll get back to that. OK, so let me just say why this sampling thing is true. Yeah, why sampling works. So you have this stream of items, and you're actually subsampling updates, positions, not the items. So this is just the same statement on the previous slide. OK, so what is the expectation of gi over p? Right, so I have fi updates. Each one is included in the sample with probability p. So it's just an unbiased estimate. It's f sub I, right? OK. What is the variance of this estimator? Variance of gi over p. So I can pull out a 1 over p squared, and I have the variance of gi. And what is that? Well, it's the sum of the variances over the updates, because I'm independently sampling. I have fi updates, and the variance for each of them is p times 1 minus p. OK, so the variance is at most, just dropping the 1 minus p, is at most the frequency fi over p. Yeah? Everyone following everything? OK, good. So now just apply Chebyshev's inequality. OK, so what's the probability that this gi over p minus fi is larger than additive epsilon m? OK, it's the variance fi over p. It's at most the variance fi over p divided by epsilon squared m squared. That's what Chebyshev's inequality gives you. P was a constant c over epsilon squared m, right? Because we want to sample 1 over epsilon squared positions. We multiply by this by m, and we get order 1 over epsilon squared. So if I plug in the value of p here, the epsilon squareds cancel. One of the m's cancels, and I get fi over c times m. OK? But now let me just union bound over all the items. OK? So the probability there exists an item I where the estimated frequency deviates from the actual frequency by more than epsilon m is just by a union bound the sum of all these probabilities, which is the sum over all items I of fi over c times m. The sum of the frequencies is the length of the stream, m, right? So this is less than 1 over c, this constant in the sampling probability. OK? This is a very, so it's a second moment argument. And so basically it says that for all items I, their frequency gi over p is within epsilon m of their actual frequency in the sample. OK, good. Yeah, so with constant probability. So as we said, the stream length is order 1 over epsilon squared after sampling. And so as we said, that means they're at most order 1 over epsilon squared distinct keys. And if we hash them pairwise independently to a universe of size 1 over epsilon to the 4th, we only need log n bits to represent this hash function. It's pairwise independent. And now the identities are also log 1 over epsilon bits. OK, so the Misra and Gries on the key value pairs now takes 1 over epsilon log 1 over epsilon bits. OK. And because of the sampling process, the heavy items in the sampled stream correspond to heavy items in the original stream. So this is a correct algorithm. The issue is, as I mentioned, that we want the original non-hash identities of the heavy hitters, right? So how do we get those? Maybe you see. Yeah, that's basically what it is. Yeah, you just basically keep 2 data structures. I mean, it's the same thing, yeah. So you have your data structure with all the hash values, right? You have your hash identities, and you have their value like in the sampled stream. But what we're also going to do is for the top 1 over phi values, as reported by our data structure, we're going to maintain their actual identities. OK? So this is a pretty big table. It's like 1 over epsilon pairs. I can't afford to maintain the actual identity of all of those things. But what I do is I just look at the top 1 over phi values. And for those values, so this is 1,000, 5,000, these are very large. For those two values, I have their actual key, okay, which is log n bits. So at any given time, for the order 1 over phi items with largest counts, as reported by our data structure, we maintain their actual log n bit identities. And the claim this is always possible to maintain in the stream, basically for the reason that when I get a new stream update, I have its actual identity, its log n bit identity. Okay, so then there's just a few cases, right? In Misra and Gries, it might be that I'm decrementing something from all the counters and I'm not inserting that new item. In that case, this item is not among the top 1 over phi items, and I do nothing. Otherwise, I might be inserting this item I into the Misra and Gries data structure. And then I just check, is its value, okay, so if it has value 1, is that value 1 amongst the top 1 over phi items? If it is, then I include its actual identity, which I have because it just got updated into this table. Yeah. So we're running Misra and Gries with 1 over epsilon. This is the hash Misra and Gries data structure. The bottom one is what it is just maintaining identities for the top. Okay, so this is Misra and Gries, and I have all these values in the key value pairs, and I look at the top 1 over phi values. For those values, I'm maintaining the actual identity, the log n bit identity. Yeah.
Question.
Yeah.
So if you have a stream in which halfway through the point, it appears, so if I have deletions and stuff.
Oh, there's no deletions. This is insertion only model. Yeah, yeah. Yeah.
Is there a 1 on phi extra complexity to do that search in the bottom?
Oh, the time complexity.
Yeah.
Yeah. So. Yeah, so basically, the short answer is we don't care. The reason is that if our stream length is sufficiently long, then I'm actually going to explain this on a slide. Then basically, for most of these updates, we're doing nothing. We're not sampling the item. So we can just spread the computation of that 1 over phi across all of these future updates. It's not even amortized. It's worst case. But let me just get back to that. Did your question? Okay, good. All right. Yeah, so it's always possible, if I have an update to the value of item I in the list, I can check if it is now amongst the top 1 over phi, and if it is, I store its identity and I throw out an identity of someone else that it replaced in the top 1 over phi. Yeah, yeah.
This still means that you have to evaluate the hash function.
You have to evaluate the hash function, but this is a constant time. I mean, it's a pairwise independent. Yeah. Oh, it's not 0 time in between these things. No. Yeah, yeah.
I was wondering if you are really implementing this beats
Okay, so yeah, an open question is about the implementation. Yeah, yeah. It's a very simple hash function, though, right? It's a pairwise independent. Well, hashing, I think what Christian means is like you have to look at the item and determine if you're going to include it or not. Is that what you mean? Or? In the sample set.
Yeah.
The stream position.
The stream position, yeah.
But why not use Witters, that hypergeometric thing that I sampled?
You just like look at, it's basically a function of positions, not of the actual value, yeah.
So you can skip, so you don't have to evaluate.
Okay, yeah. But I do have to spend, I see. I mean, I have to walk through the stream, right? Like, yeah, okay. Okay, so let me just summarize where we are. So we got 1 over epsilon, log 1 over epsilon, plus 1 over phi log n bits of space, right? Which was almost optimal. As I said, when the number of updates is large enough, you can basically make all the update times constant just by spreading out the work across enough updates, because for most stream updates, they're not sampled and we're doing nothing. Okay? Yeah, so this is just what we just discussed, okay? Okay, so the optimal algorithm, though, has space 1 over epsilon log 1 over phi plus the same 1 over phi log n. Okay, so it's a bit better than this. So the idea here is that we're spending too much space for the key value pairs in Misra Gries, right? We're spending log 1 over epsilon bits of space. So what are we going to do? Instead, we're going to do the following. We're going to run Misra Gries to find items whose frequency is at least phi times m, or phi over 2 times m. And so Misra Gries with this parameter is only going to take 1 over phi log n bits of space. Okay, it doesn't depend on epsilon. We're going to get this list of candidate heavy hitters, and we're going to use a separate data structure to estimate their individual frequencies up to additive epsilon m. And then we're going to filter out this list, okay? Make sense? So the Misra Gries data structure with just finding items that are at least frequency phi times m and no items that are frequency less than phi m over 2, say, that only takes 1 over phi log n bits of space. This separate data structure, what is it going to look like? Okay, so it's going to be log 1 over phi independent repetitions of a basic data structure. The basic data structure is going to use 1 over epsilon bits. Okay? So you know, I multiply these two quantities, I'm going to get this space bound. A question here is, what can you do with 1 over epsilon bits? Okay, it doesn't seem like enough to do much, right? So I'm trying to use this separate data structure to estimate counts of individual items that Misra Gries reports to me. Okay. Yeah, so what we want is we want to use order 1 over epsilon bits so that for any given item I, we can report an additive epsilon m approximation to its frequency with constant probability, say at least 2/3. Right, suppose we had a basic data structure that could do this. Then we have log 1 over phi independent repetitions of this data structure. And for any given I, we can take the median of the estimates reported by each of these basic data structures. Okay, by turnoff bounds, you know, each one is correct with probably 2/3. I have log 1 over phi independent repetitions. The median is going to be a correct additive epsilon m approximation with probability, say, at least 1 minus phi over 100. And how many items does this Misra Gries data structure report to me? It's going to report order 1 over phi. So I can take a union bound over all the items that it reports, and so I'll get a correct estimate for all of them. Okay? Make sense? Okay, good. Okay, so really we've reduced the problem to this basic task. Okay? So you know, what's one way of doing this? Well, we can't afford to run Misra Gries to try to get these epsilon m additive approximations. You know, so Misra Gries has 1 over epsilon counters, but for us to do this, we actually need the counters on average to only use a constant number of bits. Okay. We have some problems here, right? We can't afford to keep the item identifiers, that's log n bits. We can't even afford to keep the hash item identifiers, that's log 1 over epsilon bits. That's one problem. The other problem is we can't afford to keep exact counts, even on the sampled stream. Okay, so we have to overcome these. So dealing with item identifiers is easier. So what we do here is we're going to choose a pairwise independent hash function h from the set of all items to a universe of size 1 over epsilon items. Okay? And what we're going to do is forget about item identifiers. We're just going to, for each item, we're going to hash it to one of these 1 over epsilon values. And we're just going to treat all the items that go to a single hash value as being one meta item. You know, one item. Like I just add all the updates for a single, the same hash value. Okay, so this actually removes item identifiers. I just need to store the hash function, which is log n bits. And now I don't have to store item identifiers. Like I know exactly where each update, if I have update to item I hash it. It gives me some value here, and I just update the counter associated with that hash value. Why is that OK? Well, the expected noise in a bucket, the stuff that collides with a given item in a hash bucket, since I have 1 over epsilon hash buckets, the expected noise is epsilon times the total number of updates in the sampled stream. We're still running this on the sampled stream. OK, so the expected noise is going to be 1 over epsilon, okay, which is fine for us, because 1 over epsilon, you know, is epsilon times the sampled stream length. So, okay, so basically, we're fine with having some noise inside of our bucket, and this removes the need to store item identifiers. But what about the counts? Okay, so we still have to store counts for each of these 1 over epsilon hash buckets. So dealing with item counts. So we have R equals order 1 over epsilon counters, C1 through CR. Each counter is associated to one of these hash buckets. We know the total stream length is 1 over epsilon squared, right? We sampled down the stream. So the sum of the counts is order 1 over epsilon squared. And we want to approximate each counter up to additive error 1 over epsilon, okay? Because that's epsilon times the sampled stream length. Okay, so let me just say why this should be possible, because it's possible in the offline setting to compress these counts. So what can you do? Well, suppose I just take each count, Ci, and I round it to its nearest integer multiple of 1 over epsilon. Okay? Then I'll get additive error 1 over epsilon. And this gives order 1 over epsilon bits of space. Why? Well, what is the sum of all of these integer multiples? It's 1 over epsilon, because the sum of all the counts is 1 over epsilon squared. And I'm rounding each count to the integer multiple of 1 over epsilon. So the sum of the integer multiples is only order 1 over epsilon. So I have a sum of numbers, which is sum of integers, which is order 1 over epsilon. And I have order 1 over epsilon counts. So how many bits does it take to represent that? Well, it's like order 1 over epsilon plus 1 over epsilon, choose 1 over epsilon, the log of that, which is order 1 over epsilon bits of space. Yeah. OK. So it's possible. But how do you maintain this as the stream progresses? And I want to note here that classic, if you've seen probabilistic counters, or sometimes called Morris counters, they don't work here for a few reasons. One is that, so a probabilistic counter is a way of, so if you haven't seen this before, it's if I have a very large count in a stream, then a stream of length m, instead of using log m bits to store it exactly, I use log m bits, and I store it approximately. So that should already suggest one problem, which is that if I want a constant factor approximation to a count, I have a stream of length 1 over epsilon squared, so the probabilistic counter would take log 1 over epsilon bits. But actually, that's quite bad, because the probabilistic counter is only giving me like a constant factor approximation. And for these counts, I want some additive error 1 over epsilon. So when the count is high, the count could be as large as the stream length, 1 over epsilon squared. Then this probabilistic counter is no good. It's giving me a 2 approximation. I can adjust it to give a 1 plus epsilon approximation, but then I use even more space. So basically, this is too costly for us. If you haven't seen it, then never mind. But we can't use that. So we define what we call accelerated counters, which are the following. So to motivate the definition of an accelerated counter, let's look at the following thing that does not work. So what if we update it? We have a counter C for some frequency in a hash bucket, Fi. And suppose we update the counter with probability epsilon. Okay, so we have updates going to that hash bucket, and we're not going to update our counter every single update. It's too costly. But epsilon fraction of the updates, we are going to update our counter. Okay? You know, whatever probability I choose, I always have an unbiased estimate. The expectation of C over P is the frequency f sub I. You know, I have 1 over epsilon. I have counters that sum up to 1 over epsilon squared, and I'm keeping an epsilon fraction of these counts. So I'm really only sort of looking at 1 over epsilon updates in the stream. And so, yeah, the sum of the counts is expected to be order 1 over epsilon. And you have 1 over epsilon counters with some order 1 over epsilon. We just did this computation. That can be stored with 1 over epsilon bits. Okay? So this gives a good space solution. The problem is it's just a horrible in terms of accuracy. Okay, so imagine I have one counter, which is theta 1 over epsilon squared. I need to basically approximate it up to additive 1 over epsilon. And there's no way of doing that if I sample with probability epsilon. Okay, you can show for this you need to sample with constant probability. Okay. So this doesn't work. But it's nice it had the right space complexity. So what can we do? So when is this bad? This is bad, as I said, like when the frequency is large. Right? Because if the frequency is like 1 over epsilon squared, we want a relative error 1 plus or minus epsilon approximation. And there's no way you're going to get that by throwing away so many items. Okay, but it's precisely bad when the frequency is large. So this motivates the following notion. Suppose we knew a value r in advance, which was proportional, which is up to a constant factor equal to the frequency. Suppose we had some way of getting this. Then let's define our probability p for updating a counter to depend on the frequency itself. So with probability epsilon squared times r, I include that update in my count. Okay? So whatever probability I put here, again, the count divided by p is an unbiased estimator. That's always true. But now the variance is really nice. Why? So let's look at the variance of the count divided by p. I'm dividing by p so I can pull it out. So I have a 1 over p squared. The count, it has fi updates. And the variance is the sum of the variances. So I get fi times p1 minus p, which is fi over p. Okay, this is the same computation as before. It doesn't depend on the particular value of p. But now let's apply Chebyshev's inequality with this probability p. Okay, so what's the probability that the actual frequency minus the estimated frequency is more than 1 over epsilon? By Chebyshev's inequality, it's the variance fi over p divided by 1 over epsilon squared, so I get epsilon squared here. But now look at this probability. It actually depends on the frequency, fi. Right? Like we're accelerating the counter. So basically, as the frequency is getting larger, this probability is actually getting larger, exactly as it should be. Because for the more frequent items, we need to sample more of their items to get a 1 over epsilon additive error. So, okay, so what happens when I plug in this probability? The epsilon squareds cancel. And if r is something like 100 times the actual frequency, this thing is 1 over 100. Okay? So this actually works. The question is, well, we don't know r in advance, right? We're trying to compute the frequency. But we don't need a very good estimate. This r just needs to be a constant factor times the actual frequency for this thing to work. It's much easier to obtain constant factor approximations in the stream. Okay, so that actually works. Okay, so the solution here is, as I said, is you increase your sampling probability as your counter increases. Oh, okay. Which is sort of the opposite of standard probabilistic counters. So standard probabilistic counter, as your count is getting larger, I'm less likely to make updates to it, right? Because if my current count is 2 to the I, then I wait for 2 to the I new updates in expectation before I double it. This is actually more aggressively counting. The space bounds work out. You can get order 1 over epsilon bits of space. Basically, a frequency is fi, and its expected value is fi times p. Okay? Now, p we said was epsilon squared r. So the expected value is epsilon squared fi squared. You have 1 over epsilon squared counters. Each has expectation about this. You can show the space complexity works out. Okay? It's 1 over epsilon bits. What I didn't say is how you get this value r. And I don't have it on the slides. But you just need a constant factor approximation to a frequency at all times. And you can show if you sample 1 over epsilon stream positions, you can use these to actually have a constant factor approximation to the frequencies. Okay, so you can actually you can actually compute the sampling probability as you go in the stream. But let me skip the details. So let me just conclude here for the first part of the talk. So using these accelerated counters, we can get a space complexity which is 1 over epsilon log 1 over phi plus 1 over phi log n. Just for the same reasons as before, if the stream length is long enough, you don't do anything on most of the updates. So basically, you can spread out the computation and get update time and reporting time constant. You can show a matching lower bound. It's a standard reduction from communication complexity problem. We use the augmented indexing problem. If you're familiar with that problem. Yeah, and going back to Christian's question, we want to know if this is a significant practical improvement over Misra and Gries. And so we don't know at this point. But probably the first algorithm I presented is much more practical. But we're investigating this. But yeah.
So the first algorithm, which would just use method, that should be because you just fill it with a string. So you're doing less work.
Have people done something like this? Combining method?
No, there are papers that like look at skipped. They skip updates in a stream. So yeah, you're really just sampling 1 over epsilon squared positions.
I mean, if you do this, say, with beta, this means that you are essentially in time to read the input.
Yeah, so basically in between these, the updates that matter, you're just walking through the stream. Yeah. Yeah.
So there are algorithms like that. The question is, have they been analyzed? So what may happen is people have coded this.
Or have they been implemented, not analyzed? Or so analysis is trivial, right? Or what is?
I think the skipping over updates, people have done that. I'm not sure
Yeah.
if they have analyzed what it means and how much it's taken.
Oh, I see.
I'm trying to say people
May have not looked at just subsampling the stream. Okay, that's fair enough. Yeah.
they may not have analyzed it in the way it's
Sure, sure. Yeah, so I don't know. I mean, but yeah, the first algorithm is probably much more practical, but to be determined. So that's the end of the first part of the talk. So, all right.
All right.